Hello, I'm Professor Steve Miller. Welcome back to Compressible Flow. Today we'll be talking about off-design nozzles, that is, nozzles that are operating without isentropic flow either inside the nozzle or in the nozzle exhaust supersonically. Then we'll talk and transition this subject to shocks in nozzles and then ducts. So we previously looked at shocks inside nozzles. We'll return to that and also look at what happens with the shocks, in particular multiple converging, diverging nozzles, that is, stream tubes, in particular ducts. Then we'll return and look at the entropy temperature diagram to understand the processes of particular shock waves once again, but in a little bit more detail. Then we'll quickly show a number of examples that you're welcome to try and work through on your own. Let's get started. Sometimes I like to start with a fun quote. Here's one from none other than Professor Aurel Stodola, who's today's historical figure. And he wrote, "The country," he was talking about Germany, "is like a man with a badly upset stomach who has not yet vomited enough." And this was during the so-called Kapp-Putsch, also known as the Kapp-Ludwig-Putsch, after its leader Wolfgang Kapp and Walther von Lüttwitz. It was an attempted coup on March 1920, and this was aimed to undo the German Revolution in 1919 to overthrow the Weimar Republic and establish a right-wing autocratic government's place. Germany no doubt felt this way for many years through, of course, World War II, which was when a lot of compressible flow theory and experiments were being done leading up to the Second and during the Second World Wars by none other people like Professor Stodola. Now let's return to the nozzle problem. Here we would like to study and examine the overall pressure ratio and where the shocks reside inside Laval's nozzle. Now remember, for a fixed stagnation pressure, P0 in the plenum, or PT in the diagram of 181, upstream of the Laval nozzle, which is the converging diverging part, we will keep that constant, and then we'll decrease the back pressure ambient pressure. In practice, this happens usually in the opposite way, but to learn and understand this subject, sometimes it's a little bit easier to lower and raise back pressure and hold P0 constant for the purposes of simplicity. Now notice the overall pressure ratio, P0 over PB, the nozzle pressure ratio, NPR, that will determine the flow through the whole nozzle. The temperature ratio changes velocities typically, but it doesn't change like the general structure of the shock waves and their positions. It's relatively weak relationship there. So we can also increase P0 and fix PB to get the exact same effect. So you see it's only the ratio of the pressures that really matters and not the actual absolute values so much, as long as they're in a reasonable range. And of course we want to graph P versus X, and we've done this before. Now remember, an increase in the pressure ratio, the nozzle pressure ratio, will also increase the mass flow rate m dot through the nozzle until the nozzle chokes, as we showed earlier mathematically. Even higher NPRs will cause a normal shock to form as we raise the NPR from 1 to higher values. This is shown in the figure 182 in the lower left. Initially, we have a subsonic flow through the whole nozzle for low nozzle pressure ratio, and we have an exit Mach number less than 1. As we raise NPR to the critical pressure ratio, which is about 1.893 for gamma 1.4, a normal shock will form exactly at the throat. This normal shock, as we raise the nozzle pressure ratio even more, will be pushed from left to right in the flow direction, in this case, from the choked part of the nozzle to the nozzle exit. A slightly higher NPR will push that normal shock, of course, outside of the nozzle. And this is strange because now the shock waves will exist outside the nozzle exhaust until some particular position called the on-design position, which is only dependent on the area ratio and the Mach number. High pressure ratios, of course, will cause shock cell structures, which we'll show in a bit in this particular class, to form outside the nozzle exhaust. If we then decrease the NPR from the position where the shock wave is terminated at the nozzle exit, then of course the shock wave will move back towards the nozzle throat. And we could decrease the NPR even further until, of course, the normal shock once again arrives exactly at the normal, the throat location. Once again, the nozzle will become unchoked. So you can see this is a general operation of a nozzle where you're, of course, raising and lowering the nozzle pressure ratio, and the shock wave indeed moves upstream and downstream in the flow. Finally, again, if the NPR is reduced to unity, then the flow through the whole nozzle ceases, and essentially the nozzle or rocket type nozzle or engine is completely off. That is, you're just shutting off combustion in the chamber in practice. Now let's look at this graphically of all the possible cases that might happen in a shock with respect to pressure versus X. Now here, we will fix the total pressure, P sub T, or the total pressure or stagnation pressure, P naught. Remember this same variable. We will now vary the atmospheric pressure, P infinity. In the upper figure, we show the diagram of the flow and the possible solutions. The wall of the nozzle is the line with the ticks. The total pressure or stagnation pressure is held constant in the plenum in the upper left. And outside the engine, not in the exhaust of the flow, there's some particular back pressure or P sub infinity. In the diagrams, we'll call that P sub B, but it's really P sub infinity. Recall that we have an area of an exit and we have a choked area. And inside the nozzle, there's some possible normal shock location. The flow moves from left to right. In fact, in some cases, there's no normal shock at all in the nozzle, as you know. Now in the lower part of the figure, 184, you'll notice there's an x-axis which represents the position of the flow from the nozzle inlet to the exit and in the exhaust now. You'll also see there's some particular vertical lines. This first dashed vertical line represents the location of, indeed, the throat, and the second dashed line represents the location on X of the nozzle exit. The y-axis is representative of P, of course, the pressure normalized by total pressure. So this graph is essentially what? It's P divided by PT. Indeed, it has to be that way because, of course, pressure decreases from the total pressure where the Mach number is about 0 in the plenum. Now, for the no pressure ratio, the nozzle pressure ratio is 0 case, we'll have 0 flow. And so the flow through the whole nozzle will be, of course, P over PT is 1. Now let's say we raise our nozzle pressure ratio a tiny bit, and then we'll receive subsonic flow through the whole nozzle and in the nozzle exhaust, out here in the exhaust of the flow in the nozzle. That'll be isentropic flow, and Mach number will be less than 1 everywhere. Of course, if we raise the nozzle pressure ratio, PT over PB in this case, to 1.89 for gamma 1.4, then we'll choke the flow exactly at the sonic point at the area of the throat, and then our flow will, of course, deaccelerate back out through the nozzle to line C, which is again subsonic. Now, if I raise the nozzle pressure ratio, say 1.893 plus epsilon, then of course I will have a supersonic flow coming outside the nozzle, and it would become supersonic, at the throat in the nozzle, and it'll become supersonic where my cursor is, and then a normal shock will happen, and then the flow will come back down and exhaust supersonically. So remember, when the normal shock's in the nozzle, of course, we have subsonic flow, according to our normal shock equations and relations for standing normal shocks. If we increase the NPR a little bit more, the shock wave position will move down this curve where my cursor is, according to the on-design condition. In this case, part D, the shock wave occurs at this particular area ratio in the divergent part of the nozzle, and the pressure has a discontinuity and immediately rises, as pressure rises through shock waves, and then the flow will exhaust supersonically and pressure will continue to rise through until the nozzle exit and have subsonic flow. Indeed, we can push this shock wave all the way to point E. So if the nozzle pressure ratio pushes the shock to the nozzle exit, then we'll have subsonic flow outside the nozzle and supersonic flow completely inside the nozzle, and that's what case E is. And you can find that particular shock wave position also through the previous approach we just discussed in the previous classes. Now let's say we put the nozzle pressure ratio even a bit higher. Then what will happen? Either the flow will become supersonic through the nozzle, and indeed it will exhaust supersonically, but one of two things will happen. Either shock waves will form in the nozzle exhaust only and not in the nozzle itself, or expansion waves will form at the nozzle exit and not in the nozzle itself. These two cases are F and G, and we won't really be able to study them much until we understand the theory of expansions and shocks. There's also one more case. Imagine that we raise the nozzle pressure ratio so that the exit Mach number corresponds to the area ratio of the nozzle. In this case, the flow will be isentropic and supersonic through the whole nozzle, and the pressure P sub E at the nozzle exit is going to be approximately equal to the atmospheric pressure. Now, not exactly equal, but approximately equal in this case. And then there'll be no shocks or expansions in the nozzle exhaust. And this is the isentropic, perfectly expanded case. The condition means that P sub infinity is equal to the fully expanded pressure in the nozzle exhaust. The fully expanded pressure in the nozzle exhaust is derived from the Mach number of the ideal flow through the nozzle based on the area ratio of the nozzle, and of course the ambient pressure. So that's a P infinity, and P must be balanced with the Mach number associated with the design Mach number based on the area ratio of the nozzle. You can find those from your equations on your equations sheet. Now you can see if there's two possible nozzle, well, actually an infinite solution of different nozzle pressure ratios for supersonic flow through the nozzle, where you have shocks and expansions and shocks vice versa through the nozzle exit. These little double lines represent perhaps expansions, and these lines here, which look like little triangles up and down, hats and inverse hats, are the shear layer of the nozzle. We'll look at this more carefully later in the class. Now, it's not until many years later that, of course, people started to examine the mathematical solutions of Laval nozzles. Let's look at another family of solutions. Here we've plotted P over PT, just like in the previous graph, with X for a particular Laval nozzle. This drawing was done by Professor Luigi Crocco, which of course is a very famous compressible flow researcher. It's the same type of graph. In the upper graph, we have a choked nozzle and a family of solutions from the on-design condition, which is labeled isentropics here. And we have a family of normal shocks and isentropic flow through the Mach number at the exit, which is ideally 2.25, with a particular pressure at the exit and a separate back pressure. So this is where we have to start dividing the idea between there's a pressure at the exit of the nozzle and a back pressure, which is the ambient pressure in the atmosphere. Once again, for 0 NPR, we would have no flow, and we would raise the NPR to the critical condition, and we would have, of course, subsonic flow through the nozzle. And indeed, there's an infinite number of isentropic solutions through the nozzle for varying NPR less than the critical NPR. Once we hit that critical NPR, then we choke the nozzle. And if we raise the NPR a tiny bit, then we'll have a family of normal shockwave solutions, an infinite family of them, non-isentropic through the nozzle divergent section, which are drawn as these vertical lines with raising NPR from left to right. If we finally push the shockwave to the exit of the nozzle, then it will be pushed out into the atmosphere, and a systems of shocks and expansions will occur. Between the normal shock at the exit and the isentropic solution, we label that family of solutions as a so-called overexpanded flow outside the nozzle. It's an overexpanded flow. Now that's a very intuitive word. What does it mean by overexpanded? It means that, of course, the nozzle has pushed the pressures below that which is desirable for the nozzle expanding the flow. It's operating off design. The isentropic solution, of course, is the on-design solution. You can imagine if we raise the nozzle pressure ratio even more from the overexpanded cases, we'll have a family of underexpanded cases. That means that the nozzle has underexpanded the flow relative to the ideal on-design condition given a particular NPR, nozzle pressure ratio. Let's now look at a particular experiment, and this is why I, of course, quoted Professor Stodola, because he was the first to actually measure the flow inside these particular nozzles and confirm the mathematical theories that were laid forward by, of course, Prandtl's group in Germany. So de Laval himself did not understand the physics or indeed the mathematics of the particular nozzles he was manufacturing and selling through his dairy company. Indeed, Professor Stodola worked that out later through this particular experiment. And this is the original diagram of the Stodola experiment. And you'll notice in the upper part of the figure, this is just much like the last two figures I've shown for the nozzles, the families of solutions. Indeed, we have a nozzle wall, which is denoted by this dark black line. And it's converging, diverging, a very small converging section. And he put a single tube through the middle of his nozzle, and he could move that tube to the left and right directions. And the tube had a single static hole for static pressure. So he was able to measure P, the static pressure, anywhere in the x direction by moving this tube through the nozzle. Now, of course, the nozzle disturbed the flow itself, because, of course, it's a measurement device. And anytime you measure a flow, you disturb it. It's just like in quantum mechanics with the uncertainty principle. Here in this case, any measurement really disturbs the flow, and it's very hard to measure the values, of course, because they're changing because of the probe. And so we wouldn't expect our measurements to exactly follow the exact lines. Now, let's see here. We have a pressure at static hole, PSIA, so that's at a particular position in X for different values of nozzle pressure ratios. The x-axis here corresponds, of course, to the nozzle, and here's the line for the throat. You can see for low nozzle pressure ratios, the pressure is high, and it lowers and is high again out through the nozzle exit. And as he raises the nozzle pressure, he'll get a family of solutions where he pushes the flow, and now a normal shock has formed in the area of the nozzle throat, and it moves downstream. And you can see in this particular family, you can see how the pressure comes down. It goes through a normal shock, it rises up very abruptly, and it moves downstream. As he moved this probe downstream with higher and higher nozzle pressure ratios, he got these rises here. Now, you might say, well, the theory shows we have discontinuities in the flow, and of course the experiment shows that we have kind of smeared lines where the shocks are, like this is really a normal shock. And why is that? Take a second to think about it. Well, you might say that the normal shock, of course, has a small thickness. The pedostatic tube also has a larger thickness. The shock wave is not completely stationary, and so it's being smeared out and averaged over a particular distance in the nozzle throat. Also, of course, the theory uses an inviscid theory, and he's dealing with, of course, a viscous fluid, which is air. In all these cases contributed to, of course, this measurement problem. Today, with more accurate probes, which can measure finer pressure gradients, if you will, we can make better graphs of this. In fact, our computational fluid dynamics agrees almost perfectly with the inviscid theories relative to the experiment of Stodola. But this is the first and earliest experiment which confirmed all the mathematical theories and actually engineering devices which were being created without any understanding. Indeed, it gave a lot of credibility to the mathematical physicists in the community. Let's take a second and appreciate Professor Stodola. He was born Aurel Boleslav Stodola from 1859 to 1942. And of course, he was a Slavic engineer, physicist, and inventor. And of course, he worked in thermodynamics and published his so-called Die-Dampf turbine, the steam turbine, in 1903, which is a famous book on steam turbines. He is a professor of mechanical engineering at the Swiss Polytech Institute, which is now called ETH in Zurich. And that still exists today, and it's a very, very good university, worldwide known. In fact, one of his students was none other than Albert Einstein. And so you can see he influenced the type of thinking of literal geniuses in his time. Nonetheless, in 1892, he found the lab of energy conversion, which is where he did a lot of the work, like I showed in figure 186. And there's this picture on the right. So that's a more contemporary picture, probably in the, looking at that picture, is probably late 18 or early 1900s. So let's now take our nozzle problem and apply it to and return to the ducts with multiple throats. We last looked at this with the supersonic wind tunnel applications shown at the end of our normal isotropic module. So let's recall a few things. Here's our diagram in figure 188. The x-axis is x, the y-axis is P over PT, and we have an equivalent converging diverging nozzle with states areas 1 and 2, which may be choked in this case. And we initially have subsonic flow entering this particular duct from left to right. Now remember, if area 1 equals area 2, it will be impossible for a normal shock to exist between the throats. Why? Because of course we just learned in this module that A sup star changes in states 1 and 2, A1 sup star and A2 sup star, because of an entropy rise, such as the shock. So that would be impossible. Also, you can see that a normal shock must occur somewhere to initially initiate the supersonic flow in the tunnel. Why? Because, of course, we have to start the tunnel. And, of course, the first normal shock might appear at area 1 or area 2 if it's completely isentropic flow. Now, in practice, it always forms at area 1. Why is that? Because, of course, the shock wave will create a loss, and then the choked area of the second throat will have to be a different size, or re-choke the flow if there's enough pressure. So, therefore, to start the tunnel from a pressure ratio across the compressor of the tunnel, we will have a normal shock forming at 1 and being pushed out the initial nozzle into the test section, just like we did with, of course, the nozzle case in figure 184. So therefore, A2 must be opened up to be larger to be able to push the shock wave through the second area and not re-choke the throat. You'll see, without such a variable area geometry, it will be completely impossible to have supersonic flow through the whole test section. And so we need, indeed, a very large area at 2 to push the shock through it. This pushing of the shock through the second throat is called swallowing. Now, we might look at this picture of the second particular throat from figure 188 of the slide deck, that is at 2, blown up in sort of a cartoonish geometry, where we have a first throat where we always choke the throat. It's very small, it's the smallest area, and the second throat will be much, much larger. So what will happen when we start this particular converging diverging stream tube? Supersonic flow will obviously enter the converging diverging duct because we've choked the flow. And a normal shock will initially form at that minimum area. Of course, then we need to raise the nozzle pressure ratio, and then the flow will be supersonic in here. But since we have a converging part of the nozzle, the flow will slow down. And then it will discharge through a back pressure. And so there's a number of solutions where, as we lower the cross-sectional area of the second part of the stream tube, then we have normal shocks forming. And that's what we put through the so-called supersonic diffuser. Now we have supersonic flow through the diffuser. And to match the back pressure, we would need to have a shock wave form in this part of the flow. And so we started the tunnel and we pushed the shock wave from the first throat downstream. And by raising the nozzle pressure ratio, we push it downstream, just like we started the nozzle, and ends up somewhere in the second throat. Here's 3 possible physical situations for this, of course, to occur. The first is where the shock wave resides at some area A1, which resides in the converging part of the supersonic diffuser. It could be at A2, or it could be exactly at, which is the divergent part, or it could be exactly at the throat of the diffuser, supersonic diffuser. And we show these 3 particular situations in the graph here. Here is a particular shock wave in the conversion part. The second case is a shock wave exactly at the throat. And the third case is a shock wave in the divergent section. And you can see, indeed, that if the shock wave is at the sonic, exactly at the throat, it will result in the lowest possible back pressure. Highest possible back pressure, which is good because we would, of course, recover that. If the shock wave is before or after the throat, then we would recover a lower static pressure in the back, which is less ideal. So initially, the normal shock wave is neutrally stable at the minimum area with a back pressure of particular PBI, which means, of course, at the smallest area of the supersonic diffuser. Now, if we reduce the back pressure to PB2, what will happen? This will increase the overall pressure ratio of the whole facility, and the shock wave will move downstream to a new stable position at area 2, which would be good. The shock loss, unfortunately, would be higher because M1 in front of the shock will be higher. So you can imagine in this case, where my cursor is moving, if you're in the divergent part of the diffuser, the shock wave's here, the Mach number is higher because we've accelerated from the transonic condition to a higher Mach number. If you're shock is closer to the throat and in the divergent section, of course, it has a lower Mach number than upstream. And you would, of course, have less entropy rise and more pressure recovery. So the shock position is really determined by, indeed, the area ratios and or the back pressure. So we can start to see an idea of how we should operate our tunnels because we want to have minimal losses. In fact, you would try and minimize and adjust back pressure and area ratio of your second nozzle so it swallows it, and then of course adjust back pressure areas so that, in fact, by lowering them, they lower in the area, you would try and put your shock wave closer to the throat for lower losses. So let's try this again in a thought experiment. Suppose we start with the normal shock neutrally stable at the minimum duct area with a back pressure PPI. This is, of course, right here in the middle of the nozzle, of the supersonic diffuser, excuse me. And now we'll increase the back pressure. This will effectively decrease, of course, the pressure ratio, and the shock will move upstream to a new position at A1, which will be right here. Then, once again, the Mach number is higher, and we have subsonic flow everywhere afterwards, unless the flow is rechoked, which is very unlikely in this situation. Therefore, the losses across that shock will be even larger than, of course, the neutrally stable case at the nozzle throat. And so, therefore, in this particular situation, the back pressure, once again, cannot equal the back pressure that we desire, PB1, which is, of course, the highest static pressure. Instead, the flow will return to PB2. And you can see, since the shock wave in the divergent section of the supersonic diffuser will only give us a back pressure of PB2 and not PB1, which is what is desirable. And what does this mean? This means that the shock cannot stably stand there because, of course, we're not matching pressures. And that imbalance will, of course, accelerate the shock downstream or upstream, depending on the tunnel configuration, because the back pressures are matched. So you can see, indeed, this is what we call an unstable operating condition. It is not stable. So this means, indeed, that the stable position will result in the unstable position, will result in a pressure mismatch, which drives the shock all the way back to the upstream of the nozzle. This process is called disgorging, and it can not only happen in supersonic wind tunnels, it can also happen in particular aircraft engines. The shock is disgorged, and of course, then we would have engine unstart. If the shock is disgorged, that means it travels all the way upstream through the test section, maybe breaking our models, then we'll say that, of course, that would be like an unstart condition, and the new shock position, after it moves up the tunnel, will be located at a location which is stable with PB equal to PB1. And the shock position, of course, would go from, say, this position, A1, up to and reside somewhere in the divergent part of the tunnel. If it's moving fast enough, it could completely disgorge and go all the way out the inlet, which is what fully disgorged situation is. So in this case, we can see there's a general rule. Normal shocks can only stand stably in a diverging portion of the stream tube and not in a convergent portion. So this is a little rule of thumb you can remember, and it'll serve you well. Let's return and talk about some particular nomenclature for these different situations, just so you can remember them. The first is a block channel, and indeed this is where two throats exist in a stream tube, and the normal shock is trapped between them. And this is shown in figure 191. We have two particular areas, A1 and A2, soup-starred, and a particular shock wave is stuck. The normal shock will appear and be very unhappy and tremble or jitter, very much so, unstably, because the downstream pressure condition is generally not matched. So a block channel is where a supersonic flow exists and a shock wave is trapped between two critical areas. The second major concept we've learned is called swallowing. This means that the shock wave is pushed downstream through a second area, which must be large enough for the shock wave to pass through and rest in the divergent part of, say, the second critical throat. The final major concept is, of course, the terminal shock. The terminal shock is the particular shock wave where a shock wave or systems of shocks terminates the supersonic flow. And so, for example, in the nozzle problem, if we have a standing normal shock in the nozzle, that would indeed be the terminal shock. So the shock wave that is terminal is always the one which brings the flow back to a subsonic speed. Some more terminology. Unstart or disgorging, which we've now learned the physical concepts, is where a shock wave basically reverses its process of swallowing. So unstart or disgorging is the opposite of swallowing. A disgorged shock means it's traveling upstream through the convergent divergent stream tube and goes back up to a place where we don't want it. For example, it might fly out the front of an aircraft engine. Early aircraft engines had unstart or disgorging problems with shock waves. Or it might happen in a wind tunnel where the shock wave goes back through your test section, which is very bad, and of course damages your model. And we can talk about examples of that later in the class. Now A1 soup star over A2 soup star, that's the ratio of the first throat to the second in a two converging diverging stream tube. Or the nozzle pressure ratio or overall pressure ratio, P naught over the back pressure, that's the total pressure in front of the device divided by the ambient pressure or back pressure at the end of the device, determine when and how the shock swallowing unstart occurs. And so when we're starting up a wind tunnel or starting up an aircraft engine or rocket engine, we must be very mindful of how the shocks are swallowed or disgorged. Now the shock cannot stand stably in the convergent duct as we showed in our previous examples. So it will jump downstream rather rapidly and very fast through the divergent duct location at the back of the pressure where it's lower to, of course, balance the pressures in the flow with the back pressure. Ultimately, that's why shock waves are appearing in these cases, to balance the pressure in the flow with the back pressure, because it can't be done through other normal solutions or continuous solutions of the equations of motion. And we'll try some examples of these cases to really illustrate them later. Let's take a break from this and look at the particular temperature entropy diagrams for shocks. And this is a reminder, we've looked at this before. We have our equations of motion. Remember, we have continuity, momentum, energy, and equation of state. And so you see we have a perfect gas law. So it's a calculated perfect gas, perfect gas. Now we can imagine if we combine any three of these equations, the result describes a particular locus or point in the temperature entropy space diagram. A combination of continuity, energy, and the state equation, that's 478, 479, or 480, and 481, produces a line on the TS diagram called the Fano line or Fano flow. And we'll talk about Fano flow later in this class. This is where the momentum has dissipative terms, which is removed by friction. If we combine the continuity, momentum, and state equations, in this case it's 478, 479, and 481, then we'll have a Rayleigh line in which the heat transfer can occur. And these represent two lines, particular state 1 and 2 on the TS diagram. Now a normal shock, as we've shown, has both internal friction and heat transfer, of course, occurring in reality within it. So their initial and final states in TS space are determined by the intersection of both the Fano and Rayleigh lines, because Fano flow and Rayleigh flow has both the effect of internal friction and heat transfer. Internal friction is viscous forces, of course, for a given mass flow rate if we hold that constant. And that's what we're showing in this particular diagram. And so now we can more fully understand the particular TS diagrams for shocks. On the x-axis, we have entropy increase from S1 to S2. And the y-axis, we have temperature from T1 to 2, which increases across the shock and in Rayleigh flow and Fano flow. So in this case, you can see the shock goes directly from 1 to 2, because it's pretty much instantaneous. And the Rayleigh flow and Fano flow trace out these particular curves for various values from 1 to 2. Always, entropy must increase from the state of the equation from 1 to 2. We'll look at Rayleigh flow and Fano flow a little bit later. At this point in this class, let's just remember and summarize properties across a shock that's standing. Remember these relations and conditions to check your work as you're solving problems. If you come up with a solution and you violate any of these trends for standing normal shocks, you know you've made a mistake. Remember, velocity increases, mass flow rate is the same. The total temperature or stagnation temperature across the shock is the same. The temperature after the shock increases, the total pressure decreases, the static pressure increases, the entropy must of course increase. The density increases, and the A sub 2 sup star is larger. This is a very important point for, of course, supersonic wind tunnel operations, which we'll talk about more soon. Let's look at an example together for a particular channel or varia area stream tube with two throats. Let's walk through this example together. So in this case, we'll say a normal shock wave is blocked in a channel. And this is shown in figure 195 of the slide deck. Shock trap between two throats. We have A1 sup star, A2 sup star, and a particular area of the shock. State 1 is X and state 2 is Y, or 1 and 2 respectively. So here, throats A1 sup star and A2 sup star are choked. That means we have transonic flow, M equals 1, at A1 sup star and A2 sup star in the figure below. Now, however, A1 sup star is not equal to A2 sup star because, of course, shock exists. And you know from the normal shock relations that A2 sup star must be larger than A1 sup star because of the standing normal shock, which we just reviewed in the particular slide 594. So indeed, we'll let and have some numbers to make this a numerical example. We'll let A1 equals a meter squared, T01 is 300 Kelvin, P01 is 1010 kPa, which is 1.01 megapascal, which is a lot. And the stagnation density of the second throat, not the first, I'm changing the density measured, is 3.71 kilograms per meter cubed. In this situation, I would like us to find the area of the second throat, which is choked, and the Mach number mx ahead of the shock. Let's begin. We first seek a particular solution, A2 sup star, the area of the second throat. We need to first find the stagnation density at 1. That is the stagnation density in the first diverging stream tube, which is, of course, the stagnation density also at A1 sup star, but it's constant through that area. Now remember, we have a conservation of mass through the whole flow. M dot equals rho 1 A1 U1 equals rho 2 U2 A2. Now based on our Mach number definition, say C equals the square root of gamma RT, and C sup star equals U sup star at M equals 1, we can write U sup star equals the square root of gamma RT at the particular throat. Now remember, T1 must be equal to T2 in this case, which is T sup star, because T sup star over T naught, and T naught's constant is only a function of gamma, and M equals 1, which is constant as T naught is conserved throughout the whole flow field. Remember, T naught for a standing normal shock is conserved from X to Y in state 1 to 2, so T naught is constant through the whole flow. So therefore, T sup star must be constant and M equals 1, which of course is true at A1 sup star and A2 sup star. Therefore, we can eliminate U from the conservation of mass equation and solve for rho 1 sup star. We will then find A2 sup star over A1 sup star equals rho 1 sup star over A2 sup star. Indeed, we derived this quantity earlier in this class. All right, now we know that the stagnation gas law is conserved before the shock, and we can write P naught equals rho naught R T naught. We can fill in our values and find rho naught of 7.44 kilograms per meter cubed, of course, in the region before the shock. Now, we know that the ratios of the stagnation density to, of course, the critical densities at 1 and 2 will go as rho over 2 over rho over 1 equals rho 2 sup star divided by rho 1 sup star. And remember, at both critical conditions, M equals 1. And therefore, we can write rho 01 divided by rho 02 equals 7.44 divided by 3.71, which we just found rho 01, which will be A2 sup star over A1 sup star, which will be approximately 2. We can then find A2 sup star, which will be, of course, the area of the second throat, because, of course, we know A1 sup star, which is given our problem. We're now asked to look for the Mach number in front of the shock. Well, we know that A2 sup star over A1 sup star equals 2. We can now look for, of course, the Mach number in front of the normal shock. For a given critical area ratio has a particular Mach number. And from our compressible aerodynamics calculator or our tables, we can look up and find M in front of the shock, M1, or M sub x in this nomenclature, of 2.5. And we're done with the problem. Try and work through this problem yourself. Usually in this part of the class, I show about a 10-minute video of a supersonic flow in wind tunnels, and we'll try and show this in class together and look at it. Or you can type in this link yourself and go to about 22 minutes and 10 seconds and watch about 10 minutes of the video. In this class today, we briefly looked at the operation of nozzles with increasing and decreasing NPR, and we looked at how shock waves are pushed out to the nozzle, and we discussed and alluded to the next class of solutions we'll study, which of course is the overexpanded and underexpanded flows bounded by free shear layers, which is the wonderful and classic jet case. Then we looked at shocks inside nozzles with particular multiple throats, and we talked about a lot of basic concepts of wind tunnel operations. We'll look at these applications in wind tunnels in a forthcoming class. Then we looked at the temperature entropy diagram for Rayleigh flow, Fano flow with equations of motion. And then we showed one example, which I'll let you work through for, of course, the classic normal shock wave case, which we've done before in class. And of course, a basic example of a double choked duct, which is not normally found in practice, but it makes a great example to illustrate the difficulty and concepts of how these equations are coming together to quickly solve difficult compressible flow problems. Thank you very much for your time today. I'm Professor Steve Miller.